So I'm Ilias, Zadik, and I will talk to you about sparse high-dimensional linear regression, estimating square error and phase transition. And this is all joint work of my advisor at MIT, David Gamarnik. So I will start with introducing to you the linear regression problem. I'm sure most of you are quite familiar with it, but just to make sure we're on the same page. And then slowly I will build up the general model where I will present to you some new results we have. So what is this linear regression problem? Of course, for us it will be actually the following. There exists some vector beta star, which is the vector of coefficients, or the unknown vector that we say. And for some measurement matrix X, that's dimension n by p, and some noise vector W of dimension n, we observe n noise linear observation of this vector beta star. We put in a vector form Y that belongs in Rn, which is given by the simple formula that Y equals X beta star plus W. What is the task? The task is simple, given the knowledge of Y and X and no W, to recover beta star in some appropriate way that you define. And the notation is simple, but let's agree on this. P is the number of features of the model, and N is the number of samples. So what is the main question we'll be interested in the linear regression? It's, of course, the sample complexity, or at least, let's say, the sample complexity, which is what is the minimum M, the minimum number of samples we need to recover beta star in some general linear regression set. So, of course, you must be familiar with this question, but if you are not, a simple, very naive question under full generality would be that N should be at least P. So why is this the case? Well, because essentially you have a perturbed linear system in front of you. So in the best case, W is 0, so you have Y equals X beta star. So you have a system, a linear system with P unknowns and N equations, so you solve it, you need N to be at least P. So a lower bound should be clear in some general setting. But, well, this brings problems in the reality, as we say, the high-dimensional reality, or the Kershaw dimensionality. I don't know how you are familiar with it, because in many real-life applications, for example, in computer vision, in image processing, etc., when we try to apply linear regression, we observe much more features as samples. So we have much more pixels than images, or something like this. So when the regime, as mathematically we say, N is much less than P, and N and P are very large. So this brings naturally the question, okay, do we have a contradiction? Are we just doomed to do not use all the features, or is there a way out? And of course there is a way out. And how people go through it? Well, they put structural assumption on beta star, X and W, especially beta star. So that's what we do to design our model. We impose structural assumption on beta star. The first is the sparsity assumption, which is very common. It just assumes that we know that beta star is essentially 0 on all coordinates except a few of them. That is a subset of cardinality K. And for us, K is much less than P, and maybe K is P, actually much less than any polynomial in P for the results I will say, so assume a very low sparsity level. So this is a very classic assumption. It appears in applications, in theory, etc., etc. We'll make a second assumption, which is not that common, which is this binary coefficients. So we'll assume that every beta star has every coordinate to be either 0 or 1. So this is a less known assumption in the literature. But we did it for three reasons, especially the third one, but for three reasons. The first is it gives a discrete structure in the problem. So this makes it easier to analyze and prove actually sort of clean theorems about what is going on. The second is that it keeps the challenge of support recovery. So if you're familiar with sparse high-dimensional linear regression, you know that one of the essential tasks, and maybe one of the highly non-trivial tasks, is to find, based on the noisy linear observations, where the vector beta star is supported. What is the non-zero entries? And the support recovery is still there. Just the moment you find the support, you're essentially done. And finally, and most importantly, to the best of our knowledge, there was, or in the literature, a gap between the information theoretic lower bound, the best known one, and the best known algorithmic upper bound. So this corresponds to, there was actually a sort of more general case than this, where beta star is assumed to be in every coordinate either 0 or of magnitude at least 1, where the best known information theoretic bound and the best known algorithmic bound was like asymptotically different. So we were like interested in sort of bridging this. We'll also make some assumptions on X and W. We'll assume that X has the classic assumption. We assume that X comes with IID Gaussian, standard Gaussian entries. W is Gaussian white noise. So we'll assume that it's IID normal mean 0 variance sigma square, and sigma square is much less than K. And X and W are independent. These are classic intelligence. So in case you have mostly, let me tell you what's the model at the moment. So the model is that there exists some beta star which is binary and K sparse. And for some X, which consists of entries IID Gaussian, standard Gaussian, and W consists of entries IID mean 0 variance sigma square, random variable sigma square is much less than K, we observe n noisy linear samples, we put them in vector from Y, and Y equals X beta star plus W. And the goal is, given the knowledge of Y and X and no W, to be able to recover it with the minimum number of samples possible. And the recovery, because we have all this underlying randomness at the moment, we should have it with probability tending to 1, something we call with high probability. So what is this gap that I say? So a very brief review. So the best upper bounds, which actually work for any beta star, is known to be of the order k log p. So if n scales at least like k log p, and 2 is the best constant to the best of our knowledge that exists, is that if n scales at least like 2k log p, then lasso, base pursuit, denoising sim, orthogonal magic pursuit, iterative hard thresholding, all of them and many others work in this regime. And for some of them, there are actually negative results known for if you go below the k log p regime. So this is okay. What the best lower bound? By Wang and Wainwright in 2010, the best in the binary case now, or at least in the more general case that I said, you have serious magnitude in the non-zero coordinates, it has been proven that if n is less than n star, where n star is a threshold 2k log p divided by logarithm of k, essentially, k over sigma square, then it has been proven that there is no recovery mechanism of beta star which succeeds with high probability, recovering exactly beta star. And actually something more is easy to be proven, that if you have 1 minus epsilon here, then you cannot recover 1 minus epsilon fraction of the support of beta star if you are below this. So this is the gap here. And the natural question, the moment you see this gap, is what happens in between. And this is actually what was our interest in the talk. It will be the interest in the rest of the talk. So in particular, the question is it possible to recover it? And furthermore, is it possible to recover it efficiently? Like the specific binary problem that we have. So our results essentially that we answer yes, in some approximate way, but I think for all practical purposes to the first question. And we conjecture based on some geometrical arguments that has connection with the talk of Andrea Montanari yesterday, that the answer is no to the second. Okay, so hopefully the question is clear. So let me tell you about the first question and try, if I have time, to tell you about the second one. So about the first question, we use the MLE, which is like, I guess, the most natural thing to do. You have a problem which, for example, you care only about information, not about computational efficiency, and you say, okay, let's use the MLE. And the MLE, because you have a Gaussian white noise, has a very simple form. It just tells you it's least squares over your parameter space. So it tells you choose beta hat, which is the binary k sparse beta, that makes x beta as close to y as possible in the L2 norm. And the question is, how well does this behave? Like, is this close? Of course, it's not necessarily computationally efficient because it's an integer program, nevertheless. But how does this behave? And we're absolutely proven all or nothing theorem for it. But we need one more definition to say exactly what's the distance we use. So I will define a quantity which we call the overlap of a binary k sparse beta, or the true overlap, if you want, of a binary k sparse beta, which says that if you give me a binary k sparse beta, I will define the overlap of beta to be the cardinality of the intersection of the support of beta and the support of beta star. This is essentially the Hamming distance. I'm just telling you, give me the beta, and count how many common ones you have with beta star. And this will be our metric. Overlap is obviously between 0 and k. If overlap is close to k, you're in a very good shape. If overlap is close to 0, you're not. Okay, so our theorem from 2016 is essentially the following, that if you have n star the same that came from the Gaussian communication channel lower bound, and epsilon is arbitrary, then the moment you have 0.99, let's say n star, 1 minus epsilon n star, then with high probability the beta hat is a very bad estimator. So it's actually will find at most little o of k correct ones compared to beta star. But the moment you go slightly above the Gaussian communication channel lower bound, like 1.0001 n star, then with high probability suddenly you lose at most little o of k ones. So there is like a sharp phase transition, as we say in the behavior of this. What are the comments? Well, in particular, first of all, information exists, which is a good thing. Like the maximum likelihood estimator can find the solution if n is bigger than 1.00001 n star, let's say. There is a surface transition which we found interesting. I mean, these things exist on general in this, of course, random sort of large-scale quantities, but it's an interesting thing to see it, like here, actually, in a linear regression setting. And finally, if you care about the proof, it's actually a challenge application of the second Moe method, because we need the existence of some geometric combinatorial objects, which were actually quite challenging and I think interesting in proof-wise to sort of get. Okay, so how much time do I have now? Oh, I'm good. Okay. So let's talk about the second question. Okay, the second question is much more tricky, and we don't answer it. But we make a conjecture, and we try to prove the conjecture. It's more about a debate, I guess. So what is the question is, okay, since it was fairly easy to state at least a result where it proves that you have information in this regime, what happens? Why all the algorithms seem to fail if you go above, let's say, 2k log p? And Well, we conjecture that there is algorithmic hardness, that this is the reason. It's not our fault, like as a community, that we cannot find smart algorithms for this, but it is an inherent difficulty in the problem. So how do you argue about such a thing? That's a big question, especially in an area where complexity theory has not like emerged so far, at least in this level that exists in the worst case scenario. So we turn to random CSPs, to random constraint satisfaction problems, on actually combinatorial optimization problems under randomness. So in these problems, this picture is very actually familiar to the people there. Because it's very common, as actually we discussed also in previous talks and yesterday by Andrea, that you see at least 3 regimes in these problems. You see a regime which corresponds to a regime where, let's say, n less than n star, that you don't have information. The problem is impossible. In random case set, that corresponds, for example, that the formula is not satisfiable. You see a regime where n is bigger than a threshold, or like a corresponding parameter is bigger than a threshold, and the problem not only is easy, and not only it's possible, but it's easy as well. Like greedy algorithms perform well, local algorithms perform well. And you see a regime in between that you really don't know. You see, it is information there, the formula is satisfiable, the problem is recoverable, but you don't have efficient algorithms. So how do you argue, though, that this bound is not just trivial? Well, the random CSP community, like, actually just one paper, but there are many papers in this direction, that just I borrow this thing from them. They say turn to the geometry of the space of the solutions, and if the bounds, the thresholds are not sort of very bad, you will be able to see an important change in the geometry between the regime where information is no efficiency and information is there is efficiency. So that's what we did. We said, okay, let's turn to the geometry of the binary k-sparse vectors between these 2 regimes, and can we trace this geometrical property that changes? Furthermore, there is usually an argument that when such a property holds, no efficient algorithms exist, but when it ceases to hold, even local algorithms work, and greedy algorithms work, which is something we heard also yesterday. So there's various names for this property in the literature: shattering property, overlap gap property, and the story continues. So that's what we did. So we prove actually something that changes fundamentally, we think and we propose in the geometric way between these 2 regimes. So what is this geometric property that we prove? So informally, let's state it first. So the geometric property is in Rn. So what happens in Rn linear regression in the binary setting? What you care is essentially, because you have this binary condition, about finitely many points. So you care about y and all these x betas here, that where beta is binary. So we say that the geometric configuration of x betas around y changes a lot in these 2 regimes. So what is this change? So the overlap gap property in linear regression, we say that corresponds to the following property, that if you choose a specific, correctly adjusted radius around y, and you see all the x betas that fall inside, then we say that overlap gap property happens if these x betas shatter, essentially they split into 2 components that are disconnected in some metric very clearly. So what is this thing? We say that if you take all the x betas inside y, then you can split them into 2 groups, where you have on the one side the x betas, where betas have all very low overlap with beta star, have very, very few common ones with beta star. But if you go to the other group, you see very high overlap. Overlap is the definition I gave just before. It's like how many common ones you have with beta star. So there is like a very clear distinction. We say overlap property happen if essentially the set of beta with small distance shatter into 2 components, one with very good betas from recovered papers and one with very bad betas, and nothing in between. For example, if this property happens, you cannot find close to y in this sphere an x beta with beta of overlap k over 2, for example. Nothing medium, either very bad or very good. So formally, have the time, I guess, it is the following thing, that we say that overlap gap property happens if there exists a radius. So for a radius chart, define just what I said, all the binary k-sparse beta that fall inside this ball around y. Then at Z1 and Z2 are 2 thresholds. Then we say that the overlap gap property happens for the high dimensional linear regression if there exist 3 parameters R, Z1, Z2, so that if beta belongs in this group, the overlap is either small or large. And of course, these are not trivial statements. So there exist these 2 sets are non-empty. So what is this phase transition we prove that it happens with respect to overlap gap property? Well, we prove that if you are in this regime, then overlap gap property happens. So this is a picture that if you zoom enough, that you see this. But if you are in this regime, we lost the constants, admittedly here, C is not 2. If you go above this, and actually post-COLT we have proven and we conjecture in the COLT paper that this does not hold, finally. And Okay, in case you are sort of maybe doubting what is this essentially saying about algorithms, for example, consider local algorithms that we consider to be the best in this regime. Then actually local greedy algorithms under OGB fail. Why they fail? Well, go back to this picture. Assume you have a local search algorithm which is greedy in some sense, so it is not very sophisticated. Then what it will do, it will start with a vector that has k ones, and will just move iteratively by flipping 1, 1 to a 0 and 1, 0 to n1. And it will continue this path, and it will try to go near beta star, so in this regime. But imagine worst case, or best case, worst case, but that it starts near y in this group. Then it will, because the overlap is an integer number, it would change by at most 2. So it has a huge gap to go from here to here, so at some point it should go outside of y. And this is something that possibly a local search algorithm will never do, to increase the distance from y. And this is like a worst case analysis of like a local search algorithm that we said usually are optimal for this kind of situations. And actually we proved post-COLT that actually this local greedy algorithm works if you are above the k-log p. So it is of a fundamental possible importance. So what did I say today? I said that first of all, if n is bigger than n star, then information exists. So, okay. I said that the performance of the MLE changes suddenly when the number of samples crosses the value n star. And I said also that we conjecture that the regime is algorithmically hard, and it's not just a bad coincidence that we don't have a good algorithm, and we prove a geometrical phase transition to provide support for it. What I didn't say, what would be interesting open problems, were at least two. The question, the first, is whether we can prove that actually the MLE behavior in this regime is not arbitrary, that actually information theoretically you cannot recover any fraction of the support if you are in 0.99 n star. And it's not just that the MLE fails. And of course, then it's the algorithmic hard question, right? Because we pose it as a conjecture here. So the question is, what can we do? Can we, for example, find a reduction for the implanted click? Like in sparse PCA, can we do something like this to formulate that this is actually algorithmic hard? Okay, thank you.
So we have time for many questions, actually. So, so any question? Can you turn off the microphone?
Yes. Yes. Less than square root of p. No, I don't. I know that if k is very large, the MLE property is not true. But I don't know. It depends also. No, I'm pretty sure that actually the analysis we have certainly fails. Like in all these geometrical combinatorial arguments. Like we need at least k to be a small power of p. Like that does not hold the square root of p. But above this, I don't know. I don't want to take a conjecture like this.
So I have a quick question. So how much has the analysis, how tight is the analysis to the Gaussian assumption on the axis?
So on the axis, I think it's not that tight. I think that like it can be reduced to at least sub-Gaussian random variables, which are IID. On W, I think it's quite tight because you need this assumption of the MLE to have this.